event. So lesson 33, we're going to primarily be focusing again on the difference between independent and dependent events and how to find the probability of independent and dependent events. So what is the basic definition of simple probability? The probability of an event is equal to what? It's the number of favorable outcomes divided by the number of possible outcomes. So it's the favorable divided by possible, right? So that's kind of what we're looking at. Number of favorable outcomes divided by the number of possible outcomes. In the Bell work, there's 3 prime numbers out of the first 6 numbers, so that's 3 out of 6. Okay, 3 favorable numbers out of total numbers gives us 1/2 for that probability. So that's not going to change. But we are going to be looking at some independent events and dependent events, so we need to get a definition. Okay? Events where the outcome of one does not affect the probability of the other are called independent events. Okay, that's an important definition. The 2 events do not affect each other. They are independent of one another. Okay? To find the probability of 2 independent events, you multiply the probability of the 2 events. So it's simple. We've done some of this already. Again, this is review from your pre-algebra course. But to find the probability of 2 independent events, you're going to simply multiply the probabilities of the 2 events. Okay? Any question about the definition there of independent? So if we reverse this, what would the definition of dependent events be? This is looking ahead, but what would dependent events be? Yeah, it's 2 events where the outcome of one event does affect the probability of the other one. And we've done things like this before, so you guys are going to be good with this. But independent events, all right? Spinning a spinner and flipping a coin are independent events, right? If we're going to spin a spinner and flip a coin, those are independent events because, by definition, because what happens on this spinner has nothing to do with what happens over here. They're completely unaffected by each other, right? All right, so what is the probability then of spinning a 5? Don't answer without thinking. What's the probability of spinning a 5 and landing on heads if these 2 things are done at the same time? Griffin? 1/10. Where'd you get that from? Because the probability of spinning a 5 is 1/5. The probability of flipping a head is 1/2. And when you multiply those 2 together, you get 1/10. Okay? So this goes back to what we just said. If you have independent events, the probability of something happening or a combination of events happening is the product of the 2 different probabilities. So you find the individual probabilities and then multiply them together to get 1/10. All right, so 1/5 times 1/2 is 1/10. Is that okay? Now, what does that tell you? That there's how many favorable outcomes? 1 favorable outcome out of 10 possible outcomes. So there's 10 possible outcomes. What would the 10 possible outcomes be for these events?
1 in heads, 2 in heads, 3 in heads, 4 in heads, 5 in heads, 1 in tails, 2 in tails, 3 in tails, 4 in tails, 5.
That's it. All right, that's all the 10 possible outcomes, right? Okay, so what would the probability of an even number and heads be?
No, because it's not 6.
Probability of an even number and heads. So this would be 2 out of 5, right? That's the probability of an even number. Probability of heads is 1/2. The product of those 2 probabilities is 1/5. Okay? All right, so there's just some different questions, different way it could be asked. Okay? All right, so with dependent events, the outcome of one event does affect the probability of the other event. Okay? we've looked at these types of things before. It's where if you there's 10 marbles in a bag, different colors, and you draw one out and you don't put it back. Right? So that's going to affect every probability that's coming up because the total number of marbles has changed. Okay? To find the probability of two dependent events, you multiply the probability of the first event. Okay, so we're going to multiply again. Multiply the probability of the first event times the probability of the second, given that the result of the first event. So your second probability has been affected by the first probability. That's what it's telling you. Okay? It has to be that order. It's going to change the probability. All right, so you multiply the probability of the first event by the probability of the second event, given that the probability of the first event has happened. All right, when we look at some examples of this, you'll see it in just a second. Okay, so this is kind of a table that tells you the difference. You don't need to write this if you saw those first definitions, but independent events, the outcome does not affect the second event, and the probability is just a simple probability like that. Okay? Now, the other one, dependent events, the outcome of the first event does affect the second event, and it's still probability of the first times the probability of the second, but the probability of B is calculated under the new conditions. Okay, any questions about that? And it's going to make better sense in the context of some examples, right? But first, it's going to be helpful to us to be able to identify if an event is independent or dependent. All right, so let's just identify this as independent or dependent, and then we will calculate the probability. Rolling a 6 on a die and a 4 on another die, number cube. Independent or dependent? Completely independent, right? Two different dice are rolled. They don't affect each other. So this is an independent. What's the probability of this happening?
1/6.
So the probability of rolling a 6 on a number cube is 1/6, right? And we would multiply that by the probability of rolling a 4 on another number cube. That's 1/6.
Thought a cube had 8 sides on it.
Mm-mm.
Oh, it does.
Okay? 1/6 times 1/6 is 1/36. Okay? So 1 out of 36 would be our probability there. What about this? Karis, independent or dependent? This is not the same. The other one said rolling a 6 on a number cube and 4 on a different number cube. Are these two events independent, right? Two events. Here's one event. Here's the second event.
Is it not, will you not still get the same because you're not taking one of the options out?
Yeah, unless it said, like, unless you have, like, 6, like, glued on, you're able to, like, take it off or something.
Yeah, so we haven't really changed anything, have we? The probabilities are the same regardless of whether I roll it. It's independent. How I roll the dice, how it lands one time has nothing to do with how it's going to land the next time. So again, these are independent events, and the probability is still going to be 1 out of 36. All right? Now, drawing a red marble from a bag, keeping it out of the bag, and then drawing a blue marble. Definitely dependent, right? It's dependent because why? Explain why. Nick?
Because say you have 9 marbles in the bag, the first probability would be
Something out of 9,
something
right?
out of 9, and then the next probability would be
Something out of 8. That's exactly right. So the number of possible outcomes has been affected, and therefore it's going to change the dependence of the event. So these are dependent events. Is everybody clear on that? Dependent events. All right. Next example. What about drawing a red marble from a bag, putting it back in the bag, and then drawing a blue marble from the bag? Independent, right? Why are they independent?
Doesn't affect the sample space.
Because the That's a perfect way of saying it. The sample space has stayed the same in both events, and so the probabilities are independent of each other. Okay, so this is with replacement and without replacement. Is where you'll see this if this were a statistics book and you're talking about probabilities and statistics in a statistics standpoint. So with replacement, without replacement. If you replace the marble, then the probabilities don't change. If you don't replace it, then the probabilities are going to be affected. All right, now here's something that I want you to see, and we'll talk about it in this one context, but tree diagrams can be kind of confusing. There's a lot of possibilities. I want you to kind of think of probabilities numerically more than visually. So we're not going to really use this a lot, but some of you may be kind of familiar with it. A tree diagram can help demonstrate the sample space for events. All right, and here's an example of a tree diagram. A coin is flipped twice. Okay? Make a tree diagram to show all possible outcomes. What is the probability of the coin landing on heads both times? What's the possible outcomes here? We could have it could be tails, heads. It could be tails, tails, heads, tails,
Heads, heads.
head, head.
Landing on the side.
Okay. Anything else?
Not twice.
Is there anything else that could happen here? Do what? Well, you could make this, guys, into a diagram is just a so we could have these coin 1, coin 2, tails, 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 heads, heads, tails, heads, heads. It's just what it's called. What was the other one? Heads, heads. So what's the probability of both coins landing on heads? 1 out of 4. This is a counting type of probability, right? Is that easier?
Depends on the situation.
It does depend on the situation. There are some instances, I think, where it could be helpful, but I still think it's always going to be better to do this just using your mathematical probabilities. What's the probability of the coin landing on heads the first time?
1/2.
What's the probability of the coin landing on heads the second time? So that gives us a probability of 1/4. Okay? All right. Tree diagrams. I'm not sure what just happened. All right, Natalia has 2 squares and 3 circles in a bag. And this says without the use of a tree diagram. Find the probability of drawing a circle, keeping it, and then drawing another circle. Are these independent events or dependent events? Dependent, because the probability of the second one is affected by the outcome of the first. So, in the first drawing, what's the probability of drawing a circle? There are 3 circles and 2 squares, so 3 out of a total of 5 objects. What's the probability of keeping that and drawing another circle? So we'll just call this probability of drawing a circle. I'm going to put a little prime there because that's changed, right? Now it is 2 out of 4, which is 1/2. So the probability of these 2 events happening together is 3/5 times 2/4, or 1/2, which is 3/10. Easy enough? Okay. That's the same thing we just did, right? Okay, so Natalia, same scenario, but we're different events. The probability of drawing a square is what? Is equal to 2 out of 5. And then drawing a circle would be 3 out of 4, right? And then those probabilities, 2/5 times 3/4 would be same thing, right? 3/10. Same probability. Okay? Independent events and dependent events. All right? Odds. Did I skip a screen? Yeah, I did skip a screen. You need to write this. This is new and different. Okay? Guys, probability is defined to be favorable compared to possible in a ratio. Okay? Odds is favorable to unfavorable. Completely different way of looking at things. Okay, odds are expressed as a ratio. Usually odds are written with a colon. Okay. Usually odds are written with a colon and not in fraction form, where probabilities can also be written with a colon. Generally, odds are written with colon between the two ratios, and between the two values, and probabilities are written in fraction form. Okay, the odds of an event is a ratio expressing the likelihood of the event. Okay, the odds of the event are m to n, where m is the favorable outcome and n is the unfavorable outcomes. Now, I'm telling you right now, there's going to be some really, really simple questions that you miss on the next test because you don't read this word and recognize the difference between odds and probability. Okay? Are y'all clear on that? Okay? The word odds changes how you compute the ratio. Odds are favorable to non-favorable. What is probability? Favorable to possible. Okay? Now, and let's look at a few problems, and we'll talk about the probability, and then we'll talk about the odds so that you can see that the two things are almost always different from each other. Y'all have written what you need to write here? Good? Okay. Example 8. A bag contains 6 red marbles, 2 yellow marbles, and 1 blue marble. What are the odds? There's the important word, right? So for odds, we're talking about favorable to non-favorable. Okay? What are the odds of drawing a red marble? How many favorable outcomes are there? 6 favorable outcomes. How many non-favorable outcomes are there? 3. So that's the odds of drawing a red marble are 2 to 1. 2 to 1. What's the probability of drawing a red? 6 out of 9, right? 2/3. Are those two numbers different? Drastically different, right? Okay, so odds, and you'll hear this all the time in sports world. Right now you could go online and look at the odds for your team winning the national championship in football. What are the odds?
Very low.
Okay. Very low if you're an Ole Miss fan. Okay? All right. A bag contains 6 red marbles, 2 yellow marbles, and 1 blue marble. Now, be careful with this now. What are the odds against drawing a blue marble? The odds against 8 to 1. Okay? That's the odds against it happening. So the odds are not real good of drawing a blue marble, right? Because this is the odds against it happening. Okay? All right. Solving multi-step problems involving probability. Isaac has, and this is an interesting question. There's some homework questions that are real similar to this one, so pay attention to this. Isaac has 6 blue and 4 white shirts in his closet. Okay? 6 blue shirts, 4 white shirts. Might be a good idea at this point to stop and say there are 10 shirts. Maybe that's helpful, maybe it isn't. There are also 2 pairs of navy pants and 3 pairs of khaki pants. Okay, 2 pairs, 3 pairs, total of 5 pairs of pants. We'll kind of see this as, what is the probability Isaac will choose khaki pants and a white shirt? Khaki pants and a white shirt. Are these independent events? Yeah, I mean, we're just going to calculate the khaki pants. What's the probability that he draws khaki pants? What's the probability of khaki?
3 out of 5.
Khaki is 3 out of 5 times the probability of choosing a white shirt. 4 out of 10. So that probability is 12 out of 20, which is 6 out of 10, which is 12 out of 50, sorry. 12 out of 50. 6 out of 25. Okay? Now, 12 out of 50 might be helpful to us. Well, how is 12 out of 50 helpful to us? What does it tell us? Yeah?
That the sample space has 50 possible.
50 possible what?
Outcomes.
Outfits in this case.
Nah.
Right?
It's quite fitting.
10 pairs of pants and 5 shirts. So there's 10 ways he can choose his pants, 5 ways he can choose his shirts. Of course, there's some duplication in there, and that's where the cancelization comes and simplification comes. Okay? So 12 out of 50. But 6 out of 25 is the probability that he'll do that. Okay? Now, we could talk about something like example 11. Okay? The probability of Isaac will choose khaki pants and a white shirt from his closet is 6 out of 25. Now, this says this. We're not going to finish this problem totally. That's what we just answered. Assume that after the pants and shirts are worn, they are put in the laundry. What is the probability that he will choose khaki pants and a white shirt from the closet to wear the next day? So what changes?
There's one less white shirt. and the
Total number of shirts and the total number of pants is adjusted from the second day. So this kind of gets some layers to it. You'll have to think about what that might look like. All right? Your homework is... Man, I don't know why this thing is changing. It's not Wednesday, so... 204, A through K, and 1 through 15.
Nick, not too bad. Give me up this.
Can I please use our